All right, this is section 8.6, writing and graphing exponential decay functions. So before we learned how to do exponential growth functions, and today we're going to work with exponential decay functions. So just as a refresher, remember that those functions had an a and a b. So they were y equals a times b to the x power. And remember that b was whatever was happening. So whatever is happening to each number each time. And so in this case, it looks as though it is dividing by 4. But instead of dividing, we have to look at this as what do you multiply by? So what would you multiply by for the equivalent of dividing by 4? So the answer would be 0.25 or 1/4 would be the equivalent to dividing something by 4. And then remember A was whatever the value is when x equals 0. So in this case, our A is 1, and our B would equal 1/4. So for our function, we would have y equals 1 times 1/4 to the x power, but we don't really need that 1 because it doesn't change anything. So we can write this as 1/4 to the x power. Okay, so next we're going to look at writing a rule for this function. So when you look what's happening each time to your y value, and it looks like it's getting divided by 5, but we have to write that as a fraction. So we would say times 1/5. And then our a value is whatever x is at 0. So a in this case is 1. So again, our function would be y equals 1 times 1/5 to the x power. We don't have to have that there. So we could just say 1/5 to the x power. Okay, so for exponential decay, it's going to look like this, where it's going into the negative and decaying. A has to be greater than 0, and B has to be a number between 0 and 1 for it to be considered a decay. So we're going to graph a few of these functions. So for the first one, y equals 1/2 to the x power. So we're going to start using that XY chart that we used before. So -2, -1, 0, 1, 2. And we're going to plug those numbers in. So 1/2 raised to the -2 power would equal 4. 1/2 raised to the -1 power would be 2. 1/2 raised to the 0 power is 1. 1/2 raised to the first power is 1/2. And 1/2 raised to the second power is 1/4. So then we're going to graph those numbers. Okay. So we're going to do the same thing here, 1/5 raised to the x power. Notice our graph is a lot larger in numbers because our numbers are going to be larger. So we're going to use that same domain or those same x values. So 1/5 raised to the -2 power would be 25. I would suggest you pause the video and calculate these on your own. 1/5 raised to the -1 power is 5. 1/5 to the 0 is 1. 1/5 to the first power is 1/5, so that'd be 0.2. And 1/5 raised to the second power is 0.04. And you just get really close to 0, but you're not technically touching 0. Okay, I would like you to pause the video and graph this function. Okay, so check and make sure you have the correct answers, and make sure that your graph looks very similar. Okay, so here's a graph that's already done for us. What we're going to do is kind of make our own XY chart from this, and we're going to try to determine what the equation is. So at 0, y is at 8, and at 1, y is at 4. Okay, we could also do 2. So at 2 right here, it looks like y is at, when x equals 2, y is also at 2. So what is happening with your y values? What is happening each time? It looks like they are getting cut in half. So when they're getting cut in half, that's the same as multiplying by 1/4. So b would equal, getting cut in half would be the same as multiplying by half. So b is half. And when x equals 0, our y value is 8. So our function would be y equals 8 times 1/2 to the x power. Okay, so we just have one more example there of an exponential decay model. So this is similar to that exponential growth model that we worked with, where we had the initial amount, the decay factor, the decay rate, and then the time period, where t is the time period. Okay, so the number of acres in Ponderosa pine forest decreased in the western United States from 1963 to 2002 by 0.5% annually. In 1963, there were about 41 million acres in the pine forest. Write a function that models the number of acres in the pine forest. So we have 0.5%. If we change that to a decimal, would be 0.005. And we're starting with 41 million. Okay, so we're starting with 41 million. And we have 1 minus 0.005 to the t power for time. Okay, so the nearest tenth, about how many million acres were there in 2002? So y equals 41 million. And then 1 minus 0.005. So between 1963 to 2002, there were 39 years. So if we look at this, we're going to have to answer this in scientific notation because it's going to be too big to calculate on our calculator. So 1 minus 0.005, so 1 minus 0.005 to the 39th power would be 0.822, and then if you were to actually multiply this out, you would get a scientific notation answer of 3.37 times 10 to the 10th. So 3.37 times 10 to the 10th million acres. Okay, so then the next question is about how many will be left in 2012. So we would need to add 10 more years to this. So for 2012, we would have 41 million. And then 1 minus 0.005, and we're adding 10 years, so it would be to the 49th power. So 1 minus 0.005 to the 49th power. Okay, so this is rounded, but it would be 0.782. And I wouldn't clear your calculator, and you're going to take that times 41 million. So you get a rounded answer of 3.207 times 10 to the 10th acres would be what's left. Okay, so your assignment for this is page 535.